Hello, my name is Andrii, and I'm software developer at JetBrains, and I'm working at the Rider development team. Today, I would like to talk about the implementation of debugging functionality for Blazor WebAssembly and other types of the .NET WebAssembly applications, and how they differ from regular debugging. In addition, we will consider the anatomy and structure of such applications. A little bit about myself. At JetBrains, I'm involved in the support and improvement of the debugger for Blazor applications, anti-framework and anti-framework core tooling, as well as some features of run configurations. For example, the configuration for debugging Roslyn source generators or multi-launch configuration. In addition, I also do some open source contributions and develop my own projects in my spare time. Below, you can see the links to my social networks as well as to my blog. Let's start from the very beginning, namely, what are the members of the already not so small family of .NET WebAssembly applications. Historically, Blazor was not the first. There were some more and less well-known frameworks for Microsoft and third-party authors that made it possible to run .NET in the browser. Consider, for example, Silverlight or the more recent but already dead Bridge.NET framework. But Blazor became the first-party framework for .NET in the browser through the WebAssembly technology. I would like to know that for this talk, I will exclude the Blazor Server, Blazor United, and Blazor Hybrid frameworks because they are a topic for separate big conversations and are technically implemented very differently. Currently, Blazor WebAssembly can be used as an independent single-page application that will be hosted using the dev server that comes with .NET SDK, or if you have your own Ascent Core backend in it. According to our observation, this is the second one is the most frequently used option because Blazor is primarily about .NET full stack development rather than only front-end one. With the appearance of .NET 7, two new options appeared as part of the new new SDK workload, which allows you to build not only Blazor but also almost any .NET code in WebAssembly. Along with that, two new runtime identifiers appeared. It's browser WebAssembly and the console WebAssembly. The first is to run WebAssembly in the browser. The second is to run it within the Node.js runtime on the terminal, a local machine, or remote machine. In .NET 8, a similar workload will also appear, but for the WebAssembly system interface, a very popular standard for WebAssembly, which will make it possible to run WebAssembly code not only in the limited environment of the browser and sandbox mode, but also outside of it. For example, it allows to access the file system, network environments, system calls, and etc. WebAssembly System Interface SDK, or YC SDK, is a short-term prototype of what was already mentioned above, so it's not so relevant anymore, but it is still working. And native AT LLVM WebAssembly project is a rather experimental way to compile an application and runtime using the special scripting toolchain, which is a part of the native AT LLVM project. From the runtime lab of .NET, and into almost fully precompiled AT code. So this approach has many advantages over the convenient mono ahead of time compiler, but is currently not ready for use in real production projects. So let's move on to the first chapter. We'll look at what exactly almost any .NET Web assembly application is. Let's start with the regular Blazor WebAssembly. First, let's create a new Blazor project from the template that comes with the .NET SDK by default. And then go to newly created directory, and let's see what index.html looks like. Here you can clearly see where Blazor boots up and initializes. The principle is almost the same as in ordinary single-page applications. So we have a div with some ID, which is the framework knows about, and which is fully populated, rendered, and managed by the framework itself. And now let's build a project. And if we go to the directory containing our compiled binaries and analyze its contents, we will see several interesting files. First of all, it's blazor.boot.json. It is responsible for what dependencies the application has, the versions of these dependencies, and other less interesting posts. And among other things, we see .NET WASM, and this is our .NET runtime. Mono 1, to be more precise, which was specially compiled using app scripting into a WebAssembly binary. It is this runtime that runs the application code that we created, and in the same directory we can see the .NET.wasm file, and next to it the usual DLL dynamic library with the newly created application. You can also see the already known blazor.wassembly.js, which glues all other files together and configures the runtime. Well, now let's look at the process tree. Let's go back to the main directory of the project and let's run the application through the usual .NET run. We are interested in exactly what the processes that the framework will create after executing the launch command will look like. So using the process hacker on Windows or htop in Unix, we can build a tree, the nodes which will continue to display the command line that was used by the .NET SDK to launch relevant processes. So since we created the project from the default template, the static files with the Blazor frontend discussed earlier will be hosted using dev server, which is a regular .NET application. And this can be seen from the first arguments to .NET command, and the second argument contains the path to the application itself that needs to be launched or executed. Now let's repeat the similar experiments with the project template installed together with WASM experimental workload. For this, we need this two workload to be installed. And after that, we are able to create the project from the new template. And let's go to the folder with the project that we just created and look at the index.html file again. We see that there is no Blazor anymore, and the JavaScript code from main.js is located as a model for execution. This is very different from the Blazor approach, where we have very little control over the breakpoint launch process. Well, now it's interesting to look at main.js. We can see that here we already have some more control over what happens to our application code at startup. This allows you to make fine-tuning of settings by passing parameters to mono configuration, such as network download policy settings in the case of using WebGL. And in the case of using WebGL, it's quite simple to specify the canvas to be used for rendering, for example. And to chart the logging level of monologues, it's also possible to adjust any possible mono runtime settings like logging. And it is very important when porting the regular desktop or console application to a web one. Let's also look at the build result. So unlike Blazor, we have an app bundle directory that consists of slightly different content. A monoconfig file has appeared that is generated automatically from the project settings, and which also gives a more accurate understanding of what exactly will be performed. It immediately becomes clear that there is an entry assembly and in which directory it can be found. All DLL files move to manage directory, and next to .NET.WASM, we have the same API with the main JS, which is the entry point for the runtime API. And instead of boot.json, we have runtime config.json. Let's take a look into it. Let's remember, WASM experimental projects add a new runtime identifier, which is why the runtime config.json file was created. Such files are also created for some older .NET targets when publishing. And here you can also see a link to the entry assembly as well as to the index.html file that loads our application code into the browser page. Well, let's look at the difference in the process tree of such applications. We immediately see that the project is not started using dev server, but using an internal application called WASM app host. It is something like a server as before, but it is not installed using the .NET package, NuGet package, as it was in the Blazor where you have the server or dev server package, for example. But it's taken from the WASM experimental directory in the .NET SDK from the workload that you installed previously. It is very likely that this approach will be used for Blazor itself in future versions of the .NET SDK because it's more authentic and understandable from the point of view of tooling. And now it's clearly visible where the runtime config that we discussed earlier is used. As you can see from the command line, it is used directly when running .NET Run. And let's make intermediate summary here. Almost any .NET WebAssembly application runs with the mono runtime. This is very important to understand because despite the fact that you specify the compatible version of the language and the target framework, some C# functionality that you compile will not be understood by the runtime. A recent example is, for example, using the newest feature of generic arguments in attributes. It's okay to compile the project with such features for the WebAssembly, but at runtime it will fail because of some internal mono runtime bug because it just not applied this feature in the mono runtime itself, and you should be ready to face some issues related to runtime and compatibility. As application developers, we can configure the runtime for the required behavior. And the .NET WebAssembly applications can be distributed and in different servers. Dev server that comes with the NuGet, and the WASM app host that we have in new workload, and SMET core, your own SMET core backend that most likely you will create for your real project. And but several open questions remain. How exactly will the debugger work with our application runtime, and how will the debugger manipulate the browser and vice versa? Before revealing all the cards, let's stop at debugging a regular .NET desktop application. We have some runtime. The runtime runs the code of our application, and when the runtime starts, it waits for the debugger to connect to it, and then continues executing the code. In the case of local debugging, the debugger client is in almost the same environment as the runtime, so the lifetime of these entities is understandable and expected. But yeah, now let's move to the .NET WebAssembly applications. First of all, we have a Chromium-based browser. The browser hosts the user page in the form of tab. The tab hosts a regular WebAssembly runtime that can execute special .wasm code. The runtime starts the mono runtime, which is already able to decode and execute a common intermediate language assembly DLL file. And finally, as part of this runtime, the code that interests us from the point of view of debugging is executed. Rather complex onion-like architecture emerges, and through which the debugger needs to be able to monitor and the code execution process and receive events in reverse direction. And such a mechanism for doing so exists. It's called Debug Proxy. And in this section, we will look at it in more detail. Let's go back to the process tree. If we run it in debug, throw Rider to see the difference, we'll see a new child process. This process has some interesting arguments. First of all, this is the process ID of the parent process. It is necessary to correctly monitor the change of its state to the operation system and react accordingly. It is not of much interest to us, but DevTools URI is the one key element of work of all the stuff. Let's return to our scheme with the missing puzzle found. So now everything is in its place. Debug proxy, let's call it that for simplicity. When starting receives all the information it needs to work both with the browser tab to somehow influence and to receive events from the browser and with mono runtime, which hosts our application in itself. The intermediate level of abstraction simplifies the implementation of the debugger for the client, because now it only needs to correctly implement work with only one entity and nothing else. So let's summarize. The client does not work with the browser type directly. Debug proxy acts as a kind of communication bus between the browser, the debugger client, and the runtime. If we talk about interaction with the browser, we primarily mean the transfer of calls and events to and from the browser page, if they are not related to the .NET world. For example, information that the page has downloaded something or navigated to some URL and so on. The same applies to the calls and events from the .NET world, which do not need to be given to the browser. Unfortunately, since this is a rather specific part of the .NET SDK and is used only in the .NET in the IDE tooling domain, it does not have a stable API. And in order to maintain a correct contract, you need to research its source code. So we already know the concept of how these three components will work together. But what about the implementation? How exactly does a handshake and communication take place? It's time to talk about the protocol used when all these actors of the system communicate. So I'll start with Handshake. This is the most complex and unstable process in the entire mechanism, so it must be reviewed in small details. On the right, you can see the sequence diagram, so you don't get lost in this chaos. First of all debugger client starts a process with the application. If done correctly, .NET will figure out how to host the application. In case of ASP.NET Core, it's easier. We just take and run the backend as in the case of regular ASP.NET Core application. The infrastructure that is added using the use Blazor debugging method at the startup stage. As a result, we have Debug Proxy as in one of the previous slides with tree. After waiting for the application to start, we check this using a special HTTP health check. The debugger client start the browser in debug mode. Currently, only the Chromium family of browsers is supported because it is because of limitation on restrictions of the Debug Proxy protocol itself. It is important to make a clarification here. We launch the browser not with the actual or final page of the application, but with a special URL that we call a placeholder. We will talk about why this is needed later. At the time of startup, the browser stores the port and path in the special file inside the user's directory, which is required to create a debugger connection. After that, debugger client creates a debugging endpoint a special WebSocket URL that includes the port and path obtained after reading the file from the previous point. Having a suitable debugging endpoint, it must be given to the debug proxy so that it can be make a connection to the browser. To do this, we make a GET request, which is processed by the use Blazor debugging middleware that every Blazor backend has, and the link format used in the request may be familiar to some. The template for this request is stored in launch settings in a profile property called inspect URI. Let's go further. The Debug Proxy responds to our request as follows. It makes all the necessary connections to the browser and the monitoring time, and then returns a special status code of 302 redirect, and as well as a special URL in the response body. Having the URL from the redirect, our debugger client already creates a connection to the debug proxy. And after that, the logic begins, the implementation of which is necessary for the correct functioning of the debugger. First of all, we send over the protocol all breakpoints that were added by the user in the editor before launching the application itself. Let me remind you that we started the browser with a placeholder page or empty page, so the runtime has not yet been loaded. And therefore, the Debug Proxy will record all requests and will implement them or send them only when the monitoring time is ready to receive. If you do it differently and loaded the user page right away, we wouldn't be able to do necessary configuration in time. For example, the user set a breakpoint at the very beginning of the main method. There is a high probability that the runtime would have executed this line of code before we notified the debug proxy about the error, and it simply would not have run in time. More formally, we may receive a classical race condition here in such a case. Next, when the necessary preliminary requests have been completed, the debugger client can finally open the actual user page in the same tab instead of the placeholder. By the way, this is an example of request that is proxified into a tab and doesn't handled by Mono. As you can see, navigate is just proxified and not handled in Mono. The last step, debug proxy finished all activities related to activation of the runtimes, loading assemblies, etc., and sends a signal to the client that is ready to work. And at this point, finally, initialization can be considered complete. A moment of recap. Such a rather complex process creates the probability that anything can go wrong, and not to mention that variety of environments that can be on the user's PC. So it's very important to cover the whole Blazor debugging lifecycle with proper automated and manual testing. A workaround with placeholder pages allows us to delay the initialization of the runtime and accordingly the launch of the application code as much as we need. So there are other technologies such as sending a pause signal to the debug proxy to pause it at some point at the very beginning, but as they are not so reliable, we use them and we can't rely on it. There is one more nuance related to Chromium browsers. It's not possible to run two browsers at the same time that share the same user's profile directory. If you try to do this via the command line, the tab will open in an already existing browser. And quite often, users need to test applications in the environment of their real accounts and settings. Such cases should be tried to be correctly identified, and users should be informed about it. So, what kind of protocol itself is used that we are talking about, and why we need a WebSocket connection? So, Chromium browsers implement the so-called Chrome DevTools Protocol. Those who have worked with Selenium or other front-end test automation tool may know about it. Through this software interface, you can do almost anything with the browser and pages within the limits of the user security settings. Fortunately to us, this interface is well documented and versioned. Structurally, it consists of so-called domains or modules, and which in turn consists of types, something like a structure or record that participates in the transfer of specific data, methods or calls that the client can make to the Chromium instance. And also there are the methods that the Chromium instance sends to the client. On the right side, you can see examples. By the way, in our case, Debug Proxy is also considered as a virtual Chromium browser because the concept of connection to it is identical to Chromium. In order to consider the domains of the CDP protocol in detail, you can use the official API Explorer. The link is on the slide. Debug Proxy has some additional methods and events. There is no official standard for them, so we created our own fork of the API Explorer, which we update as soon as we find something new in the source code and update our infrastructure as well. The link is also on the slide. Now let's talk more specifically about the transport level. First of all, what is obvious, the protocol is based on WebSocket. On top of WebSocket is a somewhat informal variant of JSON RPC 2.0, which is a format for describing remote calls using JSON payloads. Also used in, for example, in Visual Studio Code and Visual Studio for as a part of the language server protocol implementation. Messages from the client are always ordered. There are three types of messages: requests, response, and events. Events are not ordered, while the requests are ordered. What is very important, you can create several so-called sessions within the single connections. This is necessary, for example, when we want to control both the browser and the browser tab at the same time without creating a new connection. Here you can see the example of payloads for requests, responses, and events. There is also the concept of a target for attaching the session. There are many types of targets. So first of all, we are interested in the browser and the page, but there are many different types of targets depending on what behavior you need when using the protocol. By default, when you create a connection, you immediately connect to the browser targets. It is not based and can have nested sessions such as pages. Finally, we can now move on to some examples of the implementation of protocol itself. First of all, it is an API that is required to create and maintain a client for CDP connection. We have developed a fairly simple SDK for it. On this slide, you can see the connection being made on the comments and the comment being sent. A comment corresponds to the method in the CDP terminology. It can be sent waiting for a response or in fire and forget mode. In this example, the setDebugger property method is called in the .NET Debugger domain, which is defined precisely in the Debugger Proxy extension to the protocol. Since almost the entire set of domains we need is supported by developers in the form of JSON specifications, we decided to write code generation to create all the necessary methods, events, and types automatically. We dispense with the use of source generators because in this case, the input data is not related to C# or Roslyn, and also because they will be updated quite rarely, and several dozen classes need to be generated for each class for each domain. which will be very frustrating for the development of it for our tooling. And we are also investigating the possibility to use incremental source generators as possible performant alternative to just console application that generates everything that we have now. The result is a lean API with minimal manual intervention. So everything is generated automatically, except the runtime of this API. So in addition to sending messages, it is also possible to listen for events, as well as create new sessions, which are called scopes. And we are trying to avoid binding to CDP terminology because we will be extending this SDK to the Firefox debugging protocol as well in the future, because Debug Proxy itself will support Firefox protocol as well. So let's go further. Here you can see the example of connection utilization already in the form of the code, and also you can see corresponding methods from the API Explorer itself. Since user-invoked methods must be ordered, they are not sent directly, but are put in the special queue, in a special long-running task in particular. So they are sent, and they are sent with assigned message ID. At the time of sending, a special task completion source is created for the same message ID and stored in a special concurrent dictionary. This source will be needed later when the API user wants to wait for a response. A separate long-running task also listens for incoming messages from the browser. They can be both events and responses to an already sent message. In the case of an event, everything is simple. We call the appropriate delegate, but in case of response to messages, we get the corresponding task completion source that we created while sending, and know its ID. And depending on whatever it is a result or an error, we set the task completion source status. Back to the examples. Breakpoints in CDP protocol work in such a way that we first send a reference, namely a file or a regular expression string with a pattern, and runtime loads different assemblies and source maps from different debug symbols one by one, as soon as it finds a candidate that matches our file name or pattern, it sends a special breakpoint result event. On the slide, you can see a simplified code example of how it's processed. It is very important to do this in a timely manner, so the IDE user does not see valid breakpoints grayed out in the editor. Processing of the logic of sending messages regarding the creation of new and deletion of old breakpoints is also done in the form of a queue. This is already due to specifics of the Debugger infrastructure in Rider. On the right, you can see a screenshot from the API Explorer page with a more detailed description of the method that we are using here. Although we did not have time to consider all the topics related to the debugger, so the logic of calculating expressions, watches, and call stacks remained outside of this talk. They are not unique from the point of view of implementation for the Blazor. So at the end, I would like to say a few words about the hot reload. The hot reload topic serves a separate conversation, but I would like to know the basic points regarding both the .NET WebAssembly and ordinary .NET application. First of all, without debugging, hot reload is already possible using .NET Watch. In addition, just a few people know, but completely competently using startup hooks and startup assemblies feature, it is possible to inject the NuGet version of .NET Watch into the runtime environment without modifying the user code. There is currently only one option for hot reload during debugging. It's edit and continue. And let's describe the edit and continue work algorithm by one point. The user somehow gets into the paused context. For example, the runtime encouraged breakpoint. Then the user makes some change in the code. Then user made some changes and finished changing and clicks continue or apply changes. The new code is compared to the old one, resulting in three very important components: the changes that occurred in the IL code, the changes that occurred in the assembly metadata, and the changes that occurred in the debug symbols. Roslyn compiler infrastructure can calculate all these variables, but it's very important to correctly track the user's actions in the virtual workspace in Rider, for example, so as not to lose even a small change. The debugger then sends the changes from the point above to the runtime. Runtime accepts these changes and to the changes the IL code itself, metadata, and PDB. And debugger sends then the breakpoints to runtime again because the old ones have already lost their relevance. And after changing the code, the user also may change the number of lines in files. So that's why it's important to update breakpoints. And now everything is ready. The debugger gives the go-ahead and code execution continues from the point in code where it stopped. And yeah, that's all. Thanks for your attention.
All right. First of all, Andrii, that is like mind-blowingly difficult and complex.
Yeah, who knew it was all quite so complicated as that?
Oh man.
So steps to get through.
Well, my favorite part of the talk was when you were showing .NET debugging, and it was like one jump to a process, and then you switched to WebAssembly debugging, and it was a labyrinth of layers. It was like,
Yeah.
it was like digging into the core of the earth. So thank you for all the work you do on WebAssembly. But I have a question for you. You were talking about .NET workloads and specifically about WASM experimental. A lot of people, when they hear the word experimental, they think, oh, this is going to be unstable. Maybe it's not production ready. From your experience implementing and working with the workload, how accurate is that experimental word when it comes to using that workload?
I think that these workloads should currently be used more in for just trying it out, because currently it's the most stable way of writing the migrating from the desktop or console one or console application into the WebAssembly world. And this workload still exists for .NET 8, but at the time of when I created this whole presentation stuff, I relied on the state of development ecosystem for the .NET 7 version of the .NET. And I think that in .NET 8, with the upcoming Blazor United and all this stuff, I think that in some way it will be made more stable and ready to use. But yeah, currently it's quite experimental. It means that it is stable to use, but the flow and the build structure and all the stuff may change. But I think that concept will remain the same.
Mm-hmm. Yeah, I know that the Byte Code Alliance is doing a lot too with the specification around WebAssembly and WASI stuff. So there's still a lot of unanswered questions when it comes to this technology. It's really stable, but I figure that's why it's experimental, because while Microsoft is doing a lot of the workload work, they're still dependent on outside parties to kind of know if anything's about to change, right? So they don't want to make any promises and guarantees in terms of this is going to be the same because they don't have control over that.
Yeah. Also,
yeah. Go
yeah,
ahead.
okay. I would like to also to mention that the biggest problem with any WebAssembly development, not only in .NET but overall, it's the standardization process, because there are a lot of features that are implemented in a lot of runtimes. Basically, it's something like from 5 to 10 different runtimes for the WebAssembly exist, and they implement different set of features, and the overall centralized standard is moving very slowly, and that's why many features implemented differently in different runtimes, and they collapse when doing it together. For example, WebAssembly threads and WebAssembly system interface threads. It's different threads model, and yeah, this is really a complex topic to correctly for people that trying to use WebAssembly, because it exists already a couple of years, but still lacks some stable standard to use.
Yeah, that's so true. Matt, do you have any specific questions?
Well, I mean, firstly, I'm surprised to see that the WebAssembly stuff is all sort of built on Mono, really, and that the .NET side of things there is using Mono, while we've kind of got a lot of very familiar with very comfortable with using the new .NET 7 and 8 versions on desktop. Is there a particular reason for that? Is it tied to the protocol that you're using, or is there any plans to move to a newer version? Do you know?
Yeah, basically regarding the runtime, regarding the Mono runtime itself, I would like to know. I think that the reason why for WebAssembly stuff Mono is used nowadays, it's because it was just simpler to port to the WebAssembly itself. So we have CoreRT and other runtimes, but when Blazor was initially created, it was simpler just to use Mono, and the only project that tries to avoid using Mono is native AT LVM project, because it uses it does not use Mono at all, and I think that maybe it will in future it will also be possible to use it in stable manner of Blazor or WebAssembly .NET development.
Because Mono is well, I guess .NET Core. To look at it that way, .NET Core is more advanced than Mono in many ways. There's I forget now who shares whether they share the garbage collector or not, but .NET Core's garbage collector obviously is cutting edge, whereas Mono I think might be older now. So it would probably benefit to move to .NET Core.
Well, I'm gonna say, well, actually, I'm gonna push up my glasses here, but Andrii maybe could elaborate on this. One of the specifications that the Bytecode Alliance is working on is a standardized garbage collector, right? So that languages like .NET or like runtimes like .NET, whether you're writing C#, F#, or VB, I guess there's still some VB people out there. If you're writing it, you don't have to bring in the garbage collector. There'll be that kind of standard garbage collection that happens across different runtimes. Is that correct in my understanding of what's happening?
Yeah, I think that in future, when the standardized way of garbage collection will be introduced in and adopted by the runtimes, I think that it makes sense, because currently a big problem for those who are trying to write some plugin system or something like that using WebAssembly as a target assembly format is that WebAssembly itself is very coupled on having the ahead of time compile stuff. So it's really hard to embed. Not all runtime supports deployment format that, for example, has Blazor currently. So when it has some mono runtime that sits and runs the .NET code, but it is not comfortable to be used in current runtimes for the WebAssembly. But and I think that in future, if this change will be adopted in some long-term perspective, it will be cool, really, because it will allow us to compile more garbage collector languages like Java or .NET or other ones without such problems.
Whoa, this is the .NET conference. Don't say the J word. Don't say it. I think we're gonna.
Don't upset the J word people here as well, though. We can all get along.
Yeah. Go ahead, Matt. I think you have a question that you wanted to ask.
Well, yeah, I mean, looking at the complexity of the internals of everything you've had to build there to get debugging working, what do you think was the most challenging problem to get it going?
Yeah, the most challenging problem is currently what I'm working on. I'm working on the hot reload support with Blazor WASM, and this is the most complex stuff here because, yeah, you know that not all parts of .NET infrastructure are open sourced ones, and it's more like reverse engineering and like dealing with the tooling as a black box. It's quite a complex one, and yeah, I think it will be really interesting experience at the end, and this is the more complex, I think.
Yeah, I mean, I guess a follow-up to your hot reload journey. You mentioned when you were talking about hot reload that a user might be working on code, they make some changes, maybe add some breakpoints, but during the proxy conversation between, say, Rider and the browser, what's passed across back to the browser is the deltas, right? Like there's like state management happening between Rider and the browser. How big are those deltas typically? Are we talking like full assemblies, or how do those deltas work?
These deltas basically, this whole technology, edit and continue, is highly limited of amount of changes that you can do without rerunning the whole application. So these deltas are basically, it's more like for changing some couple of lines inside the method, or adding maybe some simple method, something that doesn't break the overall structure of the execution code. So I think that they are quite small because in another, as you can see, for example, when you use .NET Watch for some hot reload, sometimes you see the message that you need to rerun your application and so on. And this is where a hot reload feature exceeds its limits. So yeah.
Yeah, that makes a lot of sense. I mean, I've talked to some of the folks on the Roslyn team, and just they're kind of whittling down the edge cases in terms of what code you can change that still can give you that hot reload capability. But there's still some edge cases where, like, if you remove a method completely or something like that, you just can't do that delta-ing and have to restart. So Matt has an interesting question. I think it's more around, like, I guess, different WASM runtimes and potentially debugging. So
Yes, this one's come from the chat, actually. Someone's asking, how about debugging WASM running in other environments to the browser? This all seems to be very dependent on the Chrome debug protocol. What about other environments?
Yeah, so in other environments, for example, if you're talking about console WebAssembly project, it will be slightly it will be like made in slightly different anatomy. So it will also be Debug Proxy, but the host itself will look like a browser page, but it will be actually running just running an application that can proxify some messages, because actually you could debug, for example, you see, the Chrome DevTools Protocol, it also used, for example, to debug in Node.js applications itself. So it's not tied on browser. It's more like JS ecosystem. So you can also it also enables you to debug remote targets. And so debugging the such .NET application running not in browser, or for example in Node.js, it will be done in such a way. You could just it just replaces the browser itself with an application, but the overall flow with Debug Proxy will remain the same.
Okay.
So I guess a follow-up to that then really is, do you need to build a new proxy for every environment that it runs in?
No. I think that this proxy, Microsoft made this proxy in such a way that you don't need to carry all things that they just enables you to have one single, let's say, gateway that you use, and it will just work. Ideally, yeah. So it has some issues like some breaking the JSON RPC standard or something like that, but in general, it should work like that. Yeah.
Okay. Hey, I have a follow-up question too, since we're talking about debugging. We talked a lot about Chrome and the Chrome DevTools Protocol, and I thought I heard you mention that you're working on Firefox support. I know a lot of devs love Firefox. Like, what is the big difference between, say, Chrome DevTools, Firefox, and for macOS users like Matt and I, will there ever be Safari support?
Yeah, so currently we don't have we don't spend a lot of time in this direction, because we don't see a stable support from Microsoft in Debug Proxy, and without this support we can't do anything for Firefox related. But I already investigated a bit the Firefox debugging protocol. It has some differences, but in general it's quite similar to from the DevTools protocol, just different let's say modules and stuff like that. But I think that in future it will be looking at the source code of Debug Proxy itself. It will be just the similar connection experience, but with additional switches to use the Firefox. So it has some common abstractions, common layers there, but it's more question, I think, for folks working on the Debug Proxy, because from our end, it's just we need to support the protocol, generate models, correctly calls methods, but proxy and communication will be done on their side.
Okay. Okay, very cool. But I'm definitely excited to see WebAssembly and kind of this model proliferate. I think I did a webinar. Folks can check it out on JetBrains TV with a previous guest. But one of the things I'm really excited about is the intercommunication between .NET and other ecosystems. Have you experimented with pulling in different WASM artifacts into one .NET application? So maybe one part's written with Python, one part is written with Rust, and kind of having them all operate in the same application.
Yeah, so there is a project exists that is called Extism, and this is a plugin system that was made just for that, what you're talking about. So it allows you to have a host we've implemented in one of the supported languages by WebAssembly, and have a set of plugins that could be could be written in any supported language using their PDK. And you just create a contract between them, and then you could just embed in your application different plugins in different languages. And also, as far as I know, in the one of the future releases, it will be also possible to write plugins in .NET. So currently, it's only possible to use .NET as a hosting application, but it will be also possible to write plugins in .NET, and it's very cool. It has overall idea of having such let's say, intermediate language, but not for .NET, and for a lot of languages, for Rust, for example, for language named like G word. But yeah, so it has huge potential, but yeah, currently it's also like in not so stable state. But I'm looking into it. It will be really cool, and I think that it has great potential. Yeah.
Yeah, the two things I would love to see come to .NET is a source generator that can look at a WASM file that implements the interface that's exposed in that WebAssembly artifact. And two, I'd love to see WASM supported in NuGet, so you could like add a WASM reference versus a package reference. Like that would be super cool. So
Yeah, it's a good idea.
oh, you're gonna implement it. I heard you heard it here first here, right?
Yeah. There you go, Khalid. You're over promising again. You get it the other way around.
Yeah, I'm trying to get people to make commitments here. That's what I'm trying to do. But no, I think it's great. So Andrii, this has been pretty awesome.